So, hello everyone. Yoris took us through some historic journey of his PhD time. I would like to take you all on a roller coaster journey of my current ongoing PhD journey, where I'm trying to use compact laser interferometry for displacement readout. Jan already set the floor very well, how well we have to measure the displacement motion sub-picometer, sub-femtometer region, and so on. And basically, I was trying to do this for ground-based detectors in the beginning of my PhD time, and now we think it is a good idea to include it for LGWA as well. So a quick outline. Initially, I will try to introduce the basics of laser interferometry, how we can use it as a displacement readout, then the discussion about the noise budget, can we really reach the femtometer, and in the journey we need to do some real-time signal processing, how we can track a high frequency signals and so on. Jumping into the heterodyne stabilization introduction, basically we can't just use lasers as it is for some displacement readout. The frequency noise of the laser itself will dominate. So what the idea that we use is making the laser frequency to follow some reference. We have a very stable cavity. We try to lock the laser and make the laser frequency follow the length of the cavity. In case if we have a single laser, we have cavity response that looks like dashed blue line. So every standing wave pattern, half of the wavelength, the laser frequency will resonate within the cavity. So only at that point, all the signal will get transmitted. Here you are looking at the reflected power, so you don't get anything in the resonance point. And after 180 degrees here, again, you have a resonance point. The point, if you try to directly measure this, the laser frequency is in terms of hundreds of terahertz. We don't have the capability to directly measure those. What we can do, how about using another laser, which is slightly offset by some beat note frequency. Say we have a laser at exactly 1550 nanometer and another laser with 1550 plus some delta F, some frequency, we call it as beat note frequency. Then instead of one resonance at exactly 0, we have another 2 resonance peaks, kind of, but at this point, only one laser frequency is resonating. The other one is still in off resonance state. So the signal is only to the halfway of the maximum. But you have 2 beat notes at within a FSR, the free spectral range, and this way one can kind of make use of another alternative technique where the readout scheme matches with the interferometer architecture. Disadvantage of using a single laser or so is that one can make use of boundary or Hall technique, for example, but it requires additional acousto-optic modulator. Talking about LGWA, we are very much concerned about the power consumption and additional noise that gets added up. So any additional optoelectronics that we make use of can be a source of potential noise and will limit us from going to femtometer regime. If we try to make use of the heterodyne stabilization, where shifting one frequency into another by making use of the beat note, then obviously at the point of resonance, there is this the symmetry. So just using the reflected signal as it is not possible. What we need is a nice error signal so that we can lock the laser into the cavity. Just by demodulating at this beat note frequency, we get this very nice error signal, which has a symmetrical zero crossing, and we can just lock one laser here and the other one here. I will show how this can be done in an experimental setup. So this is the proof of concept demonstration that I did in my lab. So we have 2 lasers and we create a superposition, we beat them each other and send one part to one cavity here and the other one to the other cavity. And these are all like on top of optical table experiment where no vacuum is used, no suspension. And so this is the amplitude spectral density plot, the frequency noise that we can see. Just keeping the both laser free running, don't lock them to the cavity. You have this solid line. And if at all, you just keep the cavities open to the environment, then obviously the instability, the mechanical instability in the cavity couples into the laser frequency, and you start seeing all the noises catching up into the measurement. This is what exactly we want to do in terms of displacement readout. The instability in the cavity getting into the beat note and tracking the beat note frequency gives us the information about the mirror motion. If we lock both the lasers to these two cavities, then obviously the noise gets high because both the noise from two cavities getting coupled into the system. So the proof of concept demonstration has two tunable lasers that are locked, and beat note was tracked using some commercial phase meter that is available. The disadvantage here is that, or the challenges I would call, is that the laser should be widely tunable, and when laser comes in a widely tunable region, obviously the laser itself inherently is noisy. You can't get like a very stable laser by itself if you have a wide tunability. I'm talking about a wavelength shift of above 100 nanometer or so. We don't really need it, but the laser that I am using here can go from 1510 nanometer to 1630 nanometer or so. So inherently the noise is above the Nd:YAG N-Pro lasers. And this makes difficulty in readout. So just using the commercial phase meter, which tracks the beat note between the two lasers, is very tricky. And also, if at all we need to use it for very precise measurement, obviously we need to suppress the laser frequency, and this needs a good frequency reference. Now, coming to the payload, LGWA payload, how we can use this scheme for actual displacement readout. We have two lasers as it is, we create a beat note, and we pass one of the laser into a cavity which is made up of the proof mass and a fixed mirror. Yori showed us how the proof mass will look like, and you can attach a mirror to this proof mass, and then you have another very highly stable mirror as such, and you create a cavity out of it. So this cavity is made out of proof mass and can read out the motion of the proof mass. Obviously, as I mentioned in my previous slide, we need to suppress the laser frequency noise, meaning the other arm or the other laser that we have should also be very stable. This we can do by locking the other laser to some ultra stable optical cavity. This is just an option. This can be like just a reference laser which is very, very stable, but we can also use it another optical cavity in the same cryostat or out of the seismic stations. These are all some options. This is just a sketch of how we can use it. So lock one laser to optical cavity between the proof mass and an external mirror, then the proof mass motion is encoded in the beat note between these lasers. And the disadvantage kind of is that sensing is limited in only 1 degree of freedom, where the cavity or the interferometric plane, and if at all each seismic station needs to have 2 horizontal readout, then we need another cavity made out of the other test, like another cavity in the other orthogonal direction. So in principle, this kind of readout can reach sub-femtometer noise floor, and how we can reach or what makes it really stable or really precise is discussed in the noise budget. So obviously, the first one, all we know that the laser frequency noise has this 1/f fashion, and I convert it into the from the frequency spectral density plot, I convert into length or displacement unit by using some cavity parameters, where I taken the cavity length as 5 centimeter or physical length of 20 millimeter with a refractive index for some specific reason in my lab. And I used some hemispherical configuration impedance matched cavity, and these are just the conversion factors. And obviously we use this formula to convert. And this agrees with the measured noise in the lab. So we have this initially frequency noise 1/f. Then comes the short noise. Many times we hear that just to suppress the short noise, just increase the laser frequency. This is kind of confusing because short noise by itself actually scales with the power of the laser. But what we are interested is this the signal to noise ratio. So you have DC power increase. If you increase the laser power, increases the short noise, but the information is in the demodulation signal that we use. So then you take the signal to noise ratio, and the inverse of the signal to noise ratio is what we call as short noise induced phase noise here. So also the short noise appears twice, once in locking and other time when you read out the beat. But the later one is negligible, as in this scheme, we are interested in reading out the frequency of the signal and not the actual photodiode signal by itself, or like not the amplitude of the signal. And obviously the rooms for improvement: increase the finesse, increase the laser power, the dashed line here will go down. Then temperature coupling noise. So you have a reference cavity. All the noises in the temperature noise itself can couple through the cavity, changes the length of the cavity, causes noise again. Also has 1/f trend, but I assumed some reasonable temperature noise of 1 microkelvin per square root of hertz. And also this value, that how the temperature noise gets coupled into the cavity by multiplying it with the figure of merit, is taken at the room temperature for my current measurements in the lab. So we have 1/f kind of trend. Obviously, it depends very much upon the geometry and also the involved coefficient of thermal expansions. Then we have coating thermal noise. If the cavity that we make out of the proof mass and so on, if the kind of coating that we use can be predicted, the noise can be predicted using this fluctuation dissipation theorem. So directly proportional to the temperature, increase the beam size, you go down with the noise and so on. So here I considered 99% coating and some parameters like 88 micrometer of beam width and so on. And noise is directly proportional to temperature, as I mentioned. And here it was room temperature for the current measurement, but obviously we go down by 2 orders of magnitude once the proof mass cavity is in the cryostat. Then comes some ADC readout noise. You track the beat frequency, so you have a readout mechanism that samples your signal and so on. Sampling jitter depends upon the frequency that you track, also the digitization noise. But these are these lie way down the short noise, so not so much interesting. Altogether, if we look at the effective noise floor and run a control loop, some simple integrator is enough for this model. We can suppress the laser frequency noise by many orders of magnitude. Already in the decihertz region, we are sub-picometer regime already by considering the room temperature values. And what makes it very efficient is that instead of looking at the photodiode signal as itself, we track the laser frequency. and tracking the frequency can be done in much precise way than the other. So we the digitization noise goes down. Also, we make use of the cavities. So optical resonators puts the short noise down depending upon the finesse and the value we use. So the points of noise injection in this system is in locking the laser to the proof mass cavity. How well we lock depends upon how well we can measure. Also in measuring the frequency readout or measuring the beat note. If we do these two good enough, we are good to go. What happens in some other multi-fringe interferometers? For example, deep frequency modulation interferometer or homodyne quadrature interferometers and so on. They are fundamentally limited by the readout noise because we are not tracking the frequency of the signal. Also, many of them don't use optical resonators, meaning we are quickly limited by the short noise. And in heterodyne cavity tracking, the change of frequency is proportional in proportion with the FSR of the cavity. So for example, a frequency change of 3 gigahertz corresponds to a length change of half a wavelength, so some micrometer, and we can measure frequency well of the order. The resolution is of the order of microhertz per square root of hertz. It was already shown in the LISA Phasemeter development, and so we go down by an order of 15. So in the length readout, it will be very optimistic value, meaning 10 to the power minus 22. This means that the length readout, displacement readout can be done highly precise, assuming ideal conditions. But we don't need this unrealistic values at all. What we are looking is some picometer or femtometer regime, and requires frequency stabilization in the other arm of the readout, but it is already well established. A lot of research and development is ongoing, such as locking cavities to the atomic transitions and so on. Also, a very good frequency stabilization of less than 1 hertz per square root of hertz is already achieved. So in the readout, the information is hidden in the beat note between the two lasers. So we need to track the laser frequency or the beat note frequency. How we can do is what we call as Phasemeter, a device that can track the frequency of the signal. And this is the other part I am working on. Just a introduction how this works. Say we have a signal with frequency omega, and we need to track the phase of this signal. What you do is you create a local oscillator with the same frequency, and you do the quadrature. You do the sine of the omega and cos of the omega, mix it with the input signal. Low pass filter, because you have this higher order terms, and you have in phase and out of phase signals Q and I. Some basic arithmetic trigonometry can give you the amplitude of the signal as well as phase of the signal. If at all you run this scheme in a fully phase locked loop, where you try to use a servo PID controller or so, and try to keep the Q value to 0 by adding it with the initial, then you can run this control loop, what we call as PLL, and basically this scheme tracks the frequency of the input signal. So the current frequency of the input signal is recorded in this phase increment register. How we get to know that the PLL is locked? Obviously, the Q should be close to 0, or when it is in the locked loop, and the I value, as I is the cos of the signal. If phase is 0, cos 0 goes to 1, so it should give us the amplitude of the signal. And we are working on realizing this phase meter using zinc ultrascale RF SOC. FPGA infrastructure, and these are just a schematic of what we are trying to do. So we have a in-house developed hardware coding of PLL. So basically, you kind of code each registers in it. So in this clock, the I value goes to the next register, and all these values are hardware hard coded here, and the consists of PI controller and CIC filter and so on. There is a data acquisition system that runs Yocto Linux, and real-time readout can be done using the system on chip. And we also have very high frequency data converter, high sampling data converter, which allows the real-time update of the real NCO frequency. This is already in development. This is how the board looks like. And the key features that the ADCs sample with some 4 gigahertz allows us the direct tracking of 2 gigahertz signal. And this is way above the currently known value. So detection bandwidth, if at all the proof mass moves way above the FSR or so, we do have the capability of reading, but once it is in the locking system, it should not go above gigahertz regime at all. The picometer variation of the ground motion will not give us so much of beat note frequency shift. We have a very good acquisition bandwidth and digital signal processing speed as well. So easily we can resolve microhertz frequencies as in LISA phase meter. And this is the rough measurement that I could do just the day before I started my travel here. So we have Q, we have I, and the amplitude. The I and amplitude look very similar. These are all in just bits. The units are not converted into voltages and so on. But the PIR value, here it is like a tracking of a signal generator with 1 gigahertz signal. So outlook is we are trying to continue our work on the phase meter, where we try to use the optical signal and track the heterodyne beat there, and integrate the heterodyne locking scheme into the FPGA as well. So the experimental setup that I showed had this analog locking scheme with all mixers and so on. But we don't need, we can integrate everything into this evaluation board, which makes the entire readout much simple. And we try to measure it with a very stable cavity, and then obviously probe this with a moving mirror, maybe from dual readout from 2 sides of the proof mass or so on. And the conclusion here, I just leave the questions that I showed in the very beginning, and I thank you all.
Okay. Any questions?
Yes, sweet, thanks. The cavities that you use are impedance matched. Is that a necessity? And the other question,
Right now,
and the other question there is, in your on slide 4, I see that you dump the light coming out of that impedance matched cavity. Don't you lose some information, either new information that you don't have in reflection, or just signal to noise?
Slide 4.
Yeah, this one. So you dump the transmitted light, which is probably enough light because you're impedance matched, right? Well, the first, which is more interesting because ultimately you want to shoot it onto a proof mass. And if you have all this light going through, then you have to do something with that. So my question is, do you need impedance matched cavity?
Impedance matched cavity is not a strictly necessary. We are trying to use other cavity configurations as well. But initially we had the, it was like not hemispherical cavity when I started. We were just using flat cavities. Basically, we were testing some other frequency references here. And in that case, it was easy to just commission it in the lab. But one.
So it's just because it was already there in this particular case.
Yeah.
Okay.
Any more questions?
I think there was a Zoom message.
I have a simple question.
Yeah, go ahead.
Yeah.
Shreevathsa, nice talk. I had a small query. These phase meter and the distance measurement and displacement measurements using interferometries are nice or are fantastic if your distance are very large. And I believe the intention here is to measure the small gap change between the proof mass and a frame in the case of the seismometer, right? So how does it compare with techniques like capacitance sensing or evanescence sensing in terms of residual noise? Can you throw some light how it is compared?
One thing is when you in this scheme you lock both the lasers to the cavity, so you kind of sacrifice the range. You don't have like multi-fringe readout also. You are really limited to the like the slope of the demodulated signal. So, for example, using deep frequency modulation or quadrature, homodyne quadrature, where you don't lock the laser, you have the option to do large range readout. I would say.
Not large range. I say when the two masses or the reference displacement you're trying to measure across largely separated bodies. If your bodies are very close by, for example, in the watt linkage, your moving mass and the reference frame are very close by, few millimeters or few centimeters apart. So, so how does this technique compare in terms of the residual noise? And when you use techniques like capacitance sensing or evanescent sensors, which can measure small gaps, they are not good for large separations. But for small gaps for the watt linkage, probably they can be competitive. That was my question.
Yeah, basically, this is like, sorry, this is an alternative method, right? If I understood you correctly.
My point is that since it's a space launchable thing and it'll go to the moon, how does all this complexity fetch us in comparison to a capacitance sensor, which can probably do the job, or the capacitance sensor cannot do the job at all? That was just a quick question.
I think we can't reach this level of sensitivity with capacitive sensor at all.
Okay.
There is only a way of doing interferometers here, and also this scheme, because of a different, like the architecture being the same as readout, it has a lot of advantages in this particular case, but the disadvantage is being sensitive only to a 1 degree of freedom. But
sure.
As of my understanding, nothing can go below picometer or femtometer region. Joris or Jan, any comments?
Oh yeah, I think you're right. I think if you look at the LIGO CPS, then the shortest range ones, they have high tens of picometer. And maybe if you make it even more short range, because with these things, it's always a trade-off between range and it's just a geometrical thing mostly.
Sure.
It's a trade-off between range and sensitivity. But if you want to go sub-picometer, I mean, near femtometer, then yeah, you either use light or maybe this superconductivity stuff. Right? I don't know of many other things.
Another option, like considering LGWA, we don't need to put any laser or the evaluation board of this. This will be replaced by the phase meter evaluation board, obviously, which does all the locking scheme as well as the readout. And this can be just put outside. No need of the environmental noise coupling is way less. We don't care in that region. So, and then just use the fibers to pass through the seismic stations.
Okay, thank you.
Thank you.
Go ahead, Sandeep.
Yeah, I'm done. Thank you. Thanks, Shreevathsa.
Thank you. Thank you. If there are no questions, let's thank the speaker, and we will join here at 35.